Okay, welcome back. So the purpose of this video is going to be to finish up the notes that we started in class regarding continuity and continuous functions. I gave you these properties in class to paste in your notebook, and we're not really going to do much with them except to say that if you add, subtract, multiply by a constant, or divide two functions that are continuous, the resulting function is continuous as well. This is really it. So I guess an example to that might be if you take a function that is continuous, like cosine of x, and you add a function that is also continuous, like x squared. The result, cosine of x plus x squared, would be also continuous. Same would be true if we subtracted, multiplied any of these two by a constant, or divided them, as long as you do not let the denominator equal 0. So I want to go over two examples that are a little bit more what you're going to see in terms of working with continuity. Instead of asking you if a function is continuous, this particular problem says to find the value of k that will make f of x overall continuous. So if you look at this piecewise function here, you have 3x squared minus 4x, x is less than 2, and kx plus 6 when x is greater than or equal to 2. So k here is a number, and it's not a variable. It's supposed to be some number. And our job is to find that number so that these two pieces connect. In other words, so that the function is continuous. You see, this parabola here is continuous. There's no issues with it. And this is supposed to be some line. Also no issues with it. So the only possibility is that at x equals 2, they don't meet. So we need them to meet. The question is, what does k have to be in order for these two pieces to meet? Well, if that's going to happen, this function, the x squared function, and the linear function need to be equal to each other when x is 2. In other words, the left side limit must equal the right side limit at x equals 2. And that's exactly what we're going to do. We're going to take the left side, 3x squared minus 4x, and we'll let that equal k times x plus 6. So we've set the two pieces equal to each other. And this is the part where students sometimes get confused. You don't try to solve for k now. Before that, you actually need to replace x with 2. You see, we don't need these two things to equal each other all the time. We just need them to equal each other when x is 2. And so we will replace the x's wherever you see them with 2. And that should help us solve for k. So I get 3 times 2 squared minus 4 times 2 equal to k times 2 plus 6. And it should work out really nice. So that'll be 4 times 3, 12, minus 8 equals 2k plus 6. And it becomes a real basic equation at this point. I just need to continue solving. And you see here that k must be, that's a positive 2 I'm dividing by. So k must equal negative 1. If k is negative 1, I'm guaranteed that these two pieces will meet. The second example that I want to go over is a little more complicated. It actually has two values that we're going to solve for. And I didn't type these up, I wish I had. But we're basically going to have to find the value of a and b so that f of x is continuous, overall continuous. Okay, so in this example, we are going to find two values, a and b. Now, it has 3 pieces. The function has 3 pieces instead of 2. So that means there's 2 places where the functions need to connect. This parabola needs to connect with this line when x is 1, and then this line needs to connect with this parabola when x is 4. So this means we're actually going to have 2 separate equations, similar to the previous example, but at 2 different x locations. So I'll start by trying to connect these 2 functions first, the first and the second function. So I have ax squared plus 3x. That should equal the second function, 6x plus b. And that's going to be true when x is equal to 1. So I'm going to replace x with 1, which is not going to change much. That's just a plus 3 is equal to 6 plus b. And I mean, this is not a very complicated equation, but it does have 2 different unknowns, an a and a b. I'm just going to subtract this 3, so I solve for one of them. It wouldn't have mattered, but I'm just going to go ahead and pick a since it's on the left side. So I have 3 plus b. So whatever b is, if I add 3, I get a. Okay? So I'm going to leave that alone. And then I'm come and work with the second 2, the second and the third one. I'm going to connect these. So 6x plus b is going to equal x squared plus 2. And in this case, x has to be, these 2 functions connect, or these 2 pieces connect when x is 1. Sorry, 4, when x is 4. So I'm going to replace x with 4 plus b. So that'll be 4 squared plus 2. That's 24 plus b is equal to 16 plus 2. So b is going to be 18 minus 24, negative 6. And actually, that was really nice. It worked out nice. I didn't even have to do any substitution. So it turns out that b is going to be negative 6. And so if I want to find, let me scroll down here for a little bit. If I want to find a, all I have to do now is plug in my b. So a will be 3 plus negative 6, which of course is negative 3. So there you have it. I found a and I found b. This problem just required 2 equations to solve. So that's pretty much the type of problem that you'll get when you're asked to make functions continuous. You'll get a piecewise and you have to make sure that the pieces connect at the given x values. So the last thing I want to talk about is the intermediate value theorem. And you may want to pause the video here and go ahead and copy some of this stuff down. But I'll just continue explaining. So the intermediate value theorem is one of those theorems that doesn't really allow you to do much. It's sort of an existential thing. So let's read it. If a function is continuous, so that's the condition, on a closed interval a to b, then the function takes on every value from f of a to f of b. So this a to b, these are x values, and this f of a to f of b, these are y values. So let me draw what that might look like. Let's say, for instance, that I have a function that starts at a, and let's say that it ends at b here. And let's just say that it looks something like this. Okay? What the theorem is saying is that whatever f of a is, since the function is continuous, and whatever f of b is, the function will take on every single y value between a to b, at least once. Okay? Now, I have a horizontal line that I like to use to kind of make that point. So if I can grab it, there it is. If I start at f of a, basically what the theorem says is if the function is continuous, if I move this horizontal line up along the function, I will be able to touch it at least once every single time. Sometimes I hit it 2 times. Well, here it looks like I'm hitting it 4 times. But the theorem guarantees that you hit it at least once. So for instance, if this y value were 3, and this y value, or 7, we are guaranteed that in the interval from A to B, we're going to hit every single y value between 3 and 7. So somewhere here, and we don't know exactly where, the theorem doesn't tell us where, it just tells us that for sure you're going to hit it at least once, maybe more than once. Okay, so that means somewhere there's going to be a y value on this function that has a 4, 4.1, 4.2, a 5, a 6, 6.1, 6.2, all the way up to 7. Because every single time you're able to touch this horizontal line at least once. Okay? Now, what does that mean? Does it have to hit it only once? Well, we already said no, it could be more than one time. Does it mean that it only hits y values between 3 and 7? Not really. See, the theorem guarantees that you're going to hit every y value between the interval that you have, like in this instance 3 to 7. But your function could go up, above, or below and hit other y values. The theorem doesn't speak about that at all. We don't really know. All we know is that we have every value between 3 and 7 in this case, and that's it. Okay, it could go higher, it could go lower, it could go a bunch of times up and down, and then hit 7. But we are guaranteed that at least one time we will hit all those y values. If it's not continuous, it could still work, but it's just not guaranteed. So here I have a function that is not continuous. It starts here at -5, and it's not continuous, but you see my horizontal line hits the function at least once, sometimes twice, every single time. So that means that between the -3 here to the 3, every single y value is accounted for on this graph. Now, that's what the intermediate value theorem says, but this happens to be a not continuous function. So it could still happen, but it's not guaranteed. Now here's a not continuous function, starts at -4. You see it hits it once, but here at 1, if I go between, there's nothing here. Okay, there's these y values between 1 and 4, nothing is ever, I'm not touching anything. So I go all the way to 6, but I'm not guaranteed that I'm going to hit every single y value because it is not continuous. It could happen, but it doesn't have to. So what kind of problems would we solve with this theorem? Well, here's an example. Does this function have a 0, meaning it crosses the x-axis between these 2 points? So this is sort of your interval from -3 to 0. Well, all you really have to do, since the y value at the x-axis is 0, all you have to do is go back and plug your 2 x values into your function and compare. If you get a sign change, then that means that for sure it must have crossed 0. If you don't get a sign change, then it could happen, but you're not sure that it does. So let's say I plug in f of 0. You can see that that's going to give us a +1. And f of -3, that's going to give us -27 plus 6 plus 1. And that's going to be -21 plus 1, so -20. So because at -3 we were below the x-axis at -20, and then at 0 we're above, that means that between -3 and 0, this function must have crossed the x-axis at least once. We don't know where, but we know that it crossed once. So yes. I found another problem. This is actually at a Khan Academy that I really liked. It gives you a table and it says, hey, look at this table. It gives you, it's continuous on a closed interval 1 to 6. It has to be continuous for this to work. Which intervals must have h of x equals 0? Well, if you look at the first interval, both y values are negative, so we can't really guarantee anything there. It could have crossed and then crossed back down, but we don't know that. So between 3 and 4, do you see how it changes from negative to positive? So definitely it must have hit 0 here. And then if you go from 4 to 6, it goes from positive to negative. So again, there's a sign change. So there's 2 possibilities here. So it says choose all that apply. I would definitely choose between 3 and 4. And I would definitely choose between 4 and 6. Let me erase that so you can see a little bit better those values. And that happens because you get a sign change. Now, the other intervals could have potentially had something, but we're not guaranteed. All right, that's it. See you Monday.